Welcome friends, let us go for the next part of discussion, that is spectrum. Spectrum is nothing but light is present, electromagnetic radiation is present, but the presence or absence of electromagnetic radiation has to be measured. The technical recording of the presence or absence of the electromagnetic radiation is generally said to be the spectrum, whereas presence is indicated by light, absence is indicated by dark, whereas light is having many of the measurable properties which are known as characteristic properties like wavelength, wave number, frequency. Any of the properties taken as reference, that is presence or absence with respect to wavelength, presence or absence with respect to wave number, presence or absence with respect to frequency. Thus, the technical recording of presence or absence of electromagnetic radiation or light with respect to any of its measurable property like wavelength, wave number or frequency is generally said to be the spectrum. Whereas out of these measurable properties in systematic units, the wavelength value is very little compared to the unit, that is centimeter. So therefore, except the wavelength, the remaining other, that is either wave number or frequency is taken as reference. See, when a narrow beam of white light is passed through the Nicol prism, the white light is converted to its corresponding light of 7 colors. That we can visualize the presence of 7 colors present in the normal white color light which are exposed on the screen, thus splitting, otherwise identifying the various varieties of the wavelengths, otherwise waves present in a electromagnetic radiation or the light is said to be the spectrum. Here in this case, visualization of different colors gives an idea of having of different wavelengths combination in this particular narrow beam of white light. But here also the technical recording is present, and technically recording the presence or absence of the wavelengths, we will get a complete picture, that is how many different varieties of wavelengths are present or wave numbers are present. That particular way of technically recording of electromagnetic radiation's presence or absence is said to be the spectrum. The instrument used to record the spectrum of light or electromagnetic radiation is said to be the optical spectrometer. Whereas by using this instrument, the presence or absence of the light related information is obtained on the paper in such a way that on y-axis presence or absence information, whereas on x-axis property of the wave is generally present. Presence is indicated by a bright colored information, whereas absence is indicated with the dark in color. Whereas property of wave, either wavelength, wave number or frequency is taken on the x-axis. It may be present either in increasing order or it can be present in the decreasing order. Suppose a particular wavelength is present. That particular wavelength comes in the form of a bright colored light. A particular wavelength is absent. At its corresponding position of either of its wavelength or wave number or frequency, a dark colored line will appear. Thus, presence or absence in association with which of it is present or absent is given in the form of paper on x and y axis respectively is said to be the spectrum, and the instrument used to measure the spectrum is said to be the optical spectrometer. Let us consider the spectrum, how it appears. Here on the x-axis wave number is present in the increasing order, whereas some lines are appeared. Consider these lines are bright lines, whereas the space between the lines is dark. The meaning is wherever the bright lines are appearing, those particular wave numbers are present, and remaining in between them, to what an extent the dark color is present, such kind of all waves are absent. Such an information is generally given from the spectrum. Once again I am making to your kind notice that Here on the y-axis, presence or absence. These lines, whatever are there, if you consider these are the bright lines. So bright lines indicates presence of these particular wave numbers. Remaining all are absent. Followed by whichever are present, that corresponding wave number is also indicated on the x-axis. And here the wave number is adjusted in such a way that it is increasing from left to right. Yes, with the help of the optical spectrometer, the spectrum is recorded, and the broad classification of spectrum is of following categories. Spectrum is divided into broadly two varieties. One is continuous spectrum, second one is discontinuous spectrum. Continuous implies it is homogeneous, only in one way it is going to be appearing. There is no other thing, uniformity is present. Such kind of spectrum is said to be the continuous spectrum. Here everything appears as bright. There is no other line. Everything, the total spectrum appears as just a plane of paper, bright in color. Such kind of spectrum is continuous. The total spectrum appears as complete black in background, only black background appears. Such kind of spectrum is also said to be the continuous spectrum. This is continuous emission spectrum. And this is continuous absorption spectrum. The meaning of continuous emission spectrum is all wavelengths are getting emitted, all wavelengths are present. Whatever the range we are measuring, within that range every particular wave is present. Such an information is given by the continuous. Continuous implies everything is present. Continuous emission spectrum, everything is absent. Whatever the range, the many number of waves that we are identifying, those of all waves are absent. That is said to be the continuous absorption spectrum. Whereas second half of the spectrum is discontinuous spectrum. That is not homogeneous. Some part of spectrum appears to be some portion, some way, and the other part appears in some other way. Such kind of spectrum is said to be the discontinuous spectrum. Discontinuous appears in two ways. One is discontinuous in the form of lines, discontinuous in the form of bands. Collection of lines is said to be the bands. Whereas that is also once again on behalf of nature, that is maybe an emission spectrum or it may be an absorption spectrum. Here emission spectrum and the absorption spectrums of lines we are discussing. Emission spectrum implies what? The light corresponding waves are present. Presence of wave is indicated by the bright line. So therefore the background of the spectrum is dark. Basically it is of dark background. On that dark background you will find bright colored sharp lines. The sharp lines presence of bright in color indicates presence of those particular waves. Whereas many number of waves are absent, some particular waves are present. Such kind of information is given in the form of line spectrum. That line is of emission spectrum. And reverse of that one, absorption spectrum. Absorption spectrum implies background is bright. Basically it is of bright background. On that bright background you will be finding the dark colored lines. Lines of dark are going to be appeared on the bright background. This dark colored lines indicates, consider that this is bright background followed by the dark colored lines. These dark lines indicates absence of the waves. Remaining all waves are present. Nothing but what these are all are taken by the material. Such kind of information is given in the form of absorption spectrum. These two are examples for the line spectrum. Line spectrum is generally given by the atoms. Whereas second half of the spectrum is band spectrum. That is, instead of a sharp line, collection of lines related information is present. That is, a particular band is present. So therefore that is also emission spectrum as well as the absorption spectrum. That is, background is dark, whereas on the dark background the bands of bright in color appears here or there. Such a spectrum is example for the emission type of band spectrum, and this is due to what? Molecules. And whereas absorption spectrum, background is reverse to that of emission spectrum. Background is of bright. On that bright background dark colored lines will be appeared. Dark colored collection of lines, dark colored bands will be appeared. These dark colored bands, the meaning is from this particular wave to this particular wave, some collection of nearby waves are going to be taken by the material. Such an information is present in the band spectrum of absorption type. Thus, as a whole, spectrum continuous, discontinuous. Everything is of uniform. Everything is getting emitted. Everything is getting absorbed. Whereas something is getting absorbed and something is going to be emitted. Such a spectrum is said to be the discontinuous. A particular wave is going to be given out, remaining all are absent. Whereas a particular wavelength is observed, that is absent, remaining all are present. Similarly here, collection of nearby waves, some surrounding waves are going to be given out. Surrounding waves are going to be taken by the material of the molecules is example for the band spectrum. Taken by the atoms are given out by the atoms is example for the atomic spectrum. Line spectrum, the other name of line spectrum is atomic spectrum. The other name of the band spectrum is molecular spectrum, otherwise molecule spectrum. Once again, it is very clear for you that here lines, sharp lines are responsible for a particular wave. Collection of sharp lines appears in the form of a band is responsible for the molecule related information. Atoms gives the sharp lines, whether they are taking the wavelength or they are giving out the wavelength. Those of all are indicated in the form of sharp lines. Whereas molecules connected with the bonds in between the atoms, they can take nearby wavelengths also, X, Y, Z, all are taken. So therefore here the collection of waves appears in the form of band. If they emit, it appears to be emission band spectrum. If they take up the wavelength, then there appears to be absorption band spectrum. Yes, as we discussed, there are two varieties of spectrums. One is line spectrum. Sharp lines are going to be absorbed in the spectrum. This observation leads that spectrum as line spectrum. Line spectrum is due to atoms. Atom monoatomic. Whereas collection of atoms, that is chemical combination of atoms, is molecule. Due to this chemical combination, energy levels related to the individual atoms differs slightly one from other. So therefore here, instead of sharp lines, collection of sharp lines, nothing but what? In the form of a band it appears, hence that the spectrum is said to be the band spectrum. Suppose monoatomic atom is there. As being it is monoatomic, this Y and Y dash wavelengths are getting absorbed by the atom. So therefore at the place of Y as well as Y dash, a dark colored, otherwise absence of light, remaining all is the bright, whereas here we will be getting the dark colored lines. Sharp lines are getting observed. Implies what? This line is absent. This line is taken by the atom. This line is also taken by the atom. This particular wave is taken by atom. Y dash wave is also taken by the atom. Whereas if I take the same atoms, diatomic molecule if I take, otherwise triatomic molecule if I take, instead of Y, the compared to the wavelength of, otherwise wave of Y, smaller wave as well as the bigger wave, that is X and Z are also taken by the molecule. X dash and Z dash is also taken by the molecule. So therefore instead of here a sharp line, the collection of lines appears in the form of spectrum, and this spectrum is said to be the band spectrum. Thus atoms are responsible for the sharp lines and the corresponding spectrum is said to be the line spectrum. It may be of absorption spectrum, it may be of emission spectrum. If it is absorption, on the white background we will be getting dark colored lines. If it is emission spectrum, on the black background we will be getting sharp bright colored lines we will be getting. Similar to that of the line spectrum, molecules if are present, then they will produce as the band spectrum. Once again, emission spectrum reveals the collection of bright colored bands on the dark background. Similarly, absorption spectrum gives us the dark colored bands over the bright background. Yes, spectrum and the basic recording of the spectrum involving things. See, this is the source of electromagnetic radiation, that is source of light, nothing but source of electromagnetic radiation. If the source of electromagnetic radiation is directly felt over the optical spectrometer, then the instrument used for the measuring of spectrum is said to be the recording of spectrum is said to be the optical spectrometer. Already we made the discussion. Thus, as a result, we can make the condition to record the spectrum. Suppose whatever the light felt over the optical spectrometer is taken as reference, then every particular wave of electromagnetic radiation is sensed by the optical spectrometer, and that can be giving a continuous emission spectrum appears like this. Whereas if it is set in such a way that whichever waves are not going to be sensed by the optical spectrometer are suppose kept for the recording, then everything is sensed. Then whichever are not sensed, these of all appears in the form of, see here, this is emission. Whichever lights are felt over the substance, those of all are coming in the form of bright. Whereas whichever are the opposite way of electromagnetic radiation comes in the form of continuous dark spectrum. This is continuous absorption spectrum or continuous emission spectrum. Else we make in such a way that the waves electromagnetic radiation is not felt over the optical spectrometer. As a result, spectrum is recorded, no wave is sensed, hence it appears in the form of a continuous dark spectrum, that is said to be continuous absorption spectrum. Similarly, the source of electromagnetic radiation is felt over the atom. As a result, atom absorbs some particular waves, the remaining waves will be coming out, and those of all waves are sensed by the optical spectrometer and appears in the form of the dark lines over the bright background. These particular sharp dark lines gives the information that these particular waves are taken by the atoms, that is line spectrum, atomic spectrum, and that is absorption spectrum. In the second way, when the electromagnetic radiation felt over the atom gets excited, and we will wait for some time, and the excited atom is unstable, and once again it reveals the extra amount of energy which is present in the form of its excited situation, and that particular light is felt over the optical spectrometer. Thus some particular waves will be coming out of the atom, and those appears as sharp bright colored lines on the dark background, and this is said to be the absorption spectrum of line category. Whereas if it is felt over the molecule also absorbs particular corresponding characteristic waves, thereby remaining waves are felt over the optical spectrometer and spectrum is recorded. Whichever waves are taken by the molecule, those appears in the form of dark colored collection of lines which is known as band spectrum, and this is absorption spectrum of band category. Whereas if it is felt over the molecule undergoes excitation. For that excitation process it takes some particular characteristic waves, and these waves are associated with the molecule for certain amount of time. After some time gap, these waves are given out, and the coming out waves are felt over the optical spectrometer. As a result, it gives characteristic collection of lines on the spectrum appears in the form of bright lines over the dark background, and this is example for the band spectrum, molecular spectrum of emission category. In that way, spectrum is going to be recorded, whereas every spectrum is consisting of the corresponding waves information of its corresponding characteristic parameter as either wavelength, wave number, or frequency, followed by the presence or absence. Presence is sensed by the bright in color, absence is sensed by the dark in color. For your conclusion, once again, if the electromagnetic radiation felt over the optical spectrometer, it gives a bright colored continuous spectrum. If no light, nothing but what dark is exposed over the optical spectrometer, no light is exposed over the optical spectrometer, it gives a continuous dark part, that is said to be the continuous absorption spectrum. Hydrogen spectrum. Hydrogen is the simplest atom consisting of only one electron. Such kind of hydrogen related spectrum is very simple. So therefore in the beginning, hydrogen related spectrum is recorded for the atoms of the elements, whereas a source of light, that is electromagnetic radiation, is felt over the hydrogen present in the atomic state. As a result, some of the electromagnetic radiations are taken by the hydrogen and it is getting excited and that is said to be the excited hydrogen atom, and it can stay for little amount of time because it is unstable. Whereas the unstable excited hydrogen atom emits the absorbed electromagnetic radiation. Those emitted electromagnetic radiation is felt over the optical spectrometer. As a result, it senses the waves coming out of the excited hydrogen atom, and those are recorded in the form of spectrum. And it appears in the form of bright lines over the dark background. Example for the emission spectrum, and here atom is present, and it is line spectrum, line of emission category due to atoms. Hydrogen spectrum. Balmer, the first scientist who recorded the spectrum for the atoms of elements, whereas it is recorded for the hydrogen because hydrogen is the simplest atom. As per the complexity of number of fundamental particles are concerned, hydrogen is not having any kind of neutron. Hydrogen is having one proton as well as the one electron. Hence, recording of spectrum becomes very easy. So therefore, for hydrogen, for the first time, in the visible part of electromagnetic radiation, spectrum is recorded, and that spectrum is Balmer spectrum, otherwise Balmer series. Here also, the presence or absence of the waves with respect to the characteristic property, generally wave number, otherwise wavelength is considered, that is present on x-axis is recorded. Sharp lines are observed, and these sharp lines are due to what? Emission. When the electromagnetic radiation of visible part felt over the hydrogen atoms, some part of electromagnetic radiation is taken by the hydrogen atom and it undergoes excitation. It stays at the excited situation for a short period of time. Then after it re-emits the absorbed electromagnetic radiation, and this re-emitted electromagnetic radiation is sensed by the optical spectrometer, and it appears in the form of spectrum. And that spectrum consisting of sharp lines over the dark background, and those lines from lower wave number to higher wave number are named as H alpha, H beta, H gamma, H delta lines, whereas lower energy is H alpha and the higher energies are alpha to beta to gamma to delta. The first line is H alpha line, second line is H beta, third is H gamma, fourth is H delta, etc. The corresponding wavelengths related to H alpha, H beta, gamma, delta are found to be H alpha has 6.63 Armstrong units, H beta has 4861 Armstrong units, H gamma has 4340 Armstrong units, H delta is 4102 Armstrong units, etc. The corresponding wave numbers appearing in the form of spectrum of Balmer series are as like this: presence or absence on y-axis followed by increment of wave number on x-axis. This first line appears at a wave number of 15 to 33. Second H beta line appears at 20,564. Third line H gamma line appears at 23,032, and fourth line H delta 24,372. And the last line appears in the Balmer series at a particular wave number of 27,419. This is said to be the limiting frequency of the Balmer series, that is the maximum energy involved in landing of electron from infinite energy level to the second energy level. The relevant corresponding frequency, energy or wavelength or wave number is generally said to be the limiting line. This is the limiting line. Corresponding wave number is 27,149 centimeter inverses. The first line appearing in the Balmer series, this is the first line, this is the first spectrum ever recorded, and within the first spectrum the first line appears related to the hydrogen on naming of the Balmer's related information. This line is said to be the H alpha line, and this line is H beta line, this is H gamma, H delta lines, etc., etc. Many lines are present, and this is limiting line of the Balmer series. That is, H alpha line corresponding wave number is 15,233, and corresponding wavelength, if you calculate, that is found to be 6,563 Armstrong units. Similarly, H beta, H gamma, H delta, corresponding wavelengths as well as wave numbers appearing in the Balmer part of electromagnetic spectrum recorded for hydrogen atom appears to be like this. Similar to that of Balmer, Lyman, a scientist, recorded the spectrum of hydrogen in the ultraviolet UV range, whereas that hydrogen spectrum is also emission of line category. Presents are options versus wave number and x-axis is present, whereas the corresponding lines appears to be like this first line, second line, third line, but there is no H alpha, H beta, H gamma, etc. The first line wave number is found to be 80 to 258 centimeter inverse, second line is 97 491, third line is 102 823, and the last line is 109 678 centimeter inverse. This series is said to be the Lyman series, and the last line appears to be 109 678 is said to be the limiting line of Lyman series or the Lyman spectrum. Similar to that of Balmer as well as the Lyman parts of hydrogen spectrum, in the near infrared radiation zone, middle infrared radiation zone, and the far infrared radiation zone, Fashion bracket fund also recorded the hydrogen emission line spectrum, that is atomic spectrum. Whereas in the near infrared region, the corresponding wave numbers appeared are, this is 5331 and the limiting frequency is 121.86 wave numbers are appeared. Similarly, in the middle infrared radiation zone, that is recorded by the bracket, and the series is said to be the bracket series. The first wave number appeared is 2467 and the highest wave number, limiting wave number, appears to be 6854. Similarly, in the fund series, that is in the far infrared radiation, the first line appears to be 1096 and the last line, limiting wave number, appears to be 4387. This is hydrogen related total spectrum consisting of different varieties of zones related emission characteristic features of the hydrogen atom. The broad spectrum of hydrogen includes collection of all varieties of the spectrums, that is the Lyman part, Balmer part, Fashion bracket and the fund series combination. Whereas if we observe once, here it is consisting of presence or options versus wave number in the increasing mode. Whereas at the first portion, it is having lines in the far infrared radiation, first line, second line, some other number of lines, followed by limiting line of far infrared radiation zone. Similarly, it shifts towards the middle infrared radiation zone, that is first line, second line, followed by some other lines, followed by limiting line of bracket series. Then radiation starts in the near infrared, first line, second line, followed by some other lines, with the limiting radiation of the near infrared radiation zone, that is Fashion series. Then after visible part starts, which is known as H alpha, H beta, H gamma, and the last line is limiting part of Balmer series. Then the spectrum enters into the UV part of electromagnetic zone, whereas first line, second lines are present, and the last line is said to be the limiting line of the Lyman series, which is having wave number of 109.678 centimeter inverse. The corresponding wave number is 109.678 centimeter inverse, and here the corresponding limiting lines of the Balmer is having 109.678 by 4. And this is 109.678 by 9. This is 109.678 by 16, and this is 109.678 by 25 portions. Like this, wave numbers are present for the limiting frequencies of the Lyman part, Balmer part, Fashion as well as bracket and the fund. Rydberg, by considering the orbits in the atom, a mathematical explanation was given for the wave numbers obtained in the broad spectrum of the hydrogen atom in such a way that electron de-excitation from any of the energy level to the first energy level leads to the Lyman series. Similarly, any of the energy level to the second energy level gives the Balmer series. Similarly, Fashion, bracket and the fund series. Whereas the first line, this particular line, 3 to 2 excitation, de-excitation is H alpha, and this line is said to be H beta, and this is H gamma, this is H delta, and the last one is limiting line. Like this, a mathematical explanation in the form of formula was provided by the Rydberg for all varieties of wave numbers obtained in the broad spectrum of hydrogen atom in such a way that nu bar, the wave number obtained in the broad spectrum of the hydrogen atom for different waves will becomes equal to some constant. Rydberg proposed the constant, that is Rydberg constant into 1 by n1 square minus 1 by n2 square in centimeter inverses, whereas that value is found to be 109,678 of 1 by n1 square minus n2 square in terms of centimeter inverses. So with this particular formula we can calculate the corresponding wave numbers. Otherwise all wave numbers obtained in the broad spectrum of hydrogen atom are correlated and in the form of formula represented by the Rydberg, and that formula is equal to wave number will becomes equal to 109,678 of 1 by n1 square minus 1 by n2 square in terms of centimeter inverses. Whereas in case of Lyman, n1 is equal to 1 and n2 2, 3, 4 etc up to infinity. If n2 is equal to 2, this is first line, n2 is equal to infinity, that is limiting line. Similarly, if n1 is equal to 2, n2 is equal to 3, 4, 5 up to infinity etc, this is Balmer series. Whereas 3 to 2 excitation, H alpha, H beta, H gamma respectively, and from infinity to 2 de-excitation is limiting line of Balmer series. Similarly, n1 is equal to 3 and n2 is equal to 3 plus 1, 4, 5, 6, that is said to be the near infrared fashion series. Similarly, bracket and the fund series are present. So therefore, by substituting corresponding n1 and n2 values, the wave numbers obtained in the corresponding spectrums or the broad spectrum of hydrogen atom are correlated and they will be calculated, and this particular constant is Rydberg constant, and this equation is said to be the Rydberg equation to correlate the frequencies or the wave numbers obtained in the broad spectrum of the hydrogen atom of different waves at different zones known as different series. So therefore, in calculations, Lyman is having n1 value as 1, always fixed, n2 is 2, 3, 4 up to infinity, whereas this 2 to 1 is the first line, infinity to 1 is the limiting line. Similarly, Balmer is having n1 is equal to 2, n2 3, 4, 5 up to infinity. 3 to 2 de-excitation is the first line, whereas infinity to 2 de-excitation is the limiting line. Similarly, fashion is having n1 is equal to 3, n2 is equal to 4, 5, 6 up to infinity. 4 to 3 is first line, infinity to 3 is limiting line. Similarly, bracket and the fund is having n1 is equal to 4, n2 is equal to 5 to infinity. 5 to 4 is first line, infinity to 4 is limiting line, and the fund series n1 is equal to 5, n2 is equal to 6, 7 up to infinity. 6 to 5 de-excitation is the first line, infinity to 5 de-excitation is the limiting line of the fund series. Like this, the corresponding wave numbers obtained in the broad spectrum of hydrogen atom are mathematically related with the formula, that is nu bar in terms of centimeter inverses will becomes equal to 109,678 of 1 by n1 square minus 1 by n2 square. That is said to be the Rydberg equation to calculate the various obtained wave numbers with the simple mathematical logical relation said to be the Rydberg equation, and the involved constant is known as Rydberg constant, whose value is 109,678 centimeter inverses, because in this centimeter inverses.